Assalamualaikum warahmatullahi wabarakatuh. Hmm, Sebelumnya saya mengucapkan mohon maaf untuk webinar kali ini kita selenggarakan secara tidak langsung dalam suatu bentuk webinar rekaman karena ada satu hal yang belum bisa memungkinkan untuk dilakukan secara langsung. Eh, Namun rekaman ini akan kami sharingkan di kanal YouTube Himpunan Kimia Indonesia dan juga cabang Jawa Timur dan juga ke grup-grup WhatsApp kami. Hmm, in this good occasion, we will have a talk from Dr. Hao Wu. Uh, Let me share the backgrounds of Dr. Hao Wu. So, Dr. Hao Wu is assistant professor in the Department of Material Science and Engineering, Faculty of Innovation Engineering, Macau University of Science and Technology. Uh, he's He got his Ph.D. degree from the University of New South Wales under supervision of Rose Amals, someone that we really appreciate in the photocatalytic field. Also, his supervisor is also Professor Yun Hao Ong. His teaching area and include the energy materials, green catalysis, solar energy conversion and storage, as well as instrumental analysis, in which his research area concentrates on the photoactive semiconductors, hydrogen production, charge dynamics, photocatalysis, and photoelectrochemical sensors. Previously, Dr. Hao Wu works as a postdoctoral programs in the School of Energy and Environment, City University of Hong Kong, under supervision of Professor Yun Hao Eng. Until 2022, he moved to the Macau University of Science and Technology in Macau, China, as the assistant professor. Dr. Hao Wu has published papers and articles in very reputable journals like Advanced Energy Material in 2023, but I remember he just recently published some papers even in the Nature Communications and many reputable papers. You can see his uh, profiles in his web group website that we can search online. I'm sure that we are used to search online anyway. For now, let's start our talks with Dr. Hao. Hmm. Dr. Hao,
Yep.
uh,
Can you hear? Can you hear me?
yes, we can hear
Oh,
you, and the
great.
time is yours.
Thank you. I'm gonna just share my screen. So it should be okay to see the screen, right? I'm gonna play with it. So thanks for the kind introduction by Dr. Utomo, Wahyu. And also it's a great pleasure to be joining this webinar organized for Indonesia Chemical Society, its Java branch. So I will introduce that my name is Hao, and currently I'm a faculty member at Macau University of Science and Technology. And today mix of oxide semiconductors in solar field production. But before my talk, I would like to share a bit more about my institute, and university. So our institute is relatively young, which was established in 2021, and the name is Macau Institute of Material Science and Engineering, which was founded by the Fellow of Chinese Academic Science and also the Fellow of World Academic Science, Professor Shutang Li, which is a very well-known research scientist in photoelectrical conversion materials. And our university is located in Macau, which is very close to Hong Kong. Macau is a very modern city, which combined with the mixed cultures, like with Eastern and Western cultures, and which is very beautiful, But however, the Macau is very small, with very limited space. So for our institute, that we extend our research institute into the mainland of China, called Hengqin Island, which is very close to Macau. If we take the car, maybe only 15 to 20 minutes drive, we can go to the Macau from our institute in Hengqin. Our institute in Hengqin is very beautiful. We can see that there we have a very beautiful mountain on the back. We can hike on there over the weekend. We can also do jogging over the river. So the environment is pretty good. And meanwhile, I would like also acknowledge or introduce my research group. So I established my group in Macau around 2022, and our name is Solar Energy Electrochemical Catalysis Analysis Team, called CCAT. So with the 3 years of development, now we have around 14 group members, including myself, and also we have postdocs, PhDs, and we also join PhD programs with Suzhou University or City University of Hong Kong, and also we have 6 master students. So with their inputs, it helped us to do some wonderful research programs together. So this is basically the background introduction, and now then we will go to the story about the solar fuel production together. So we're talking about solar fuel production, which is a process that focuses on photoelectrocatalysis, or we call artificial photosynthesis, which is a process that mimics nature, harvests the intermediate sunlight, and convert the carbon dioxide into solar fuels. When talking about photosynthesis, actually, nature has done a very good job. That's why we can see the plant on the earth can harvest the sunlight and convert the carbon dioxide from the air, water from the soil into sugars, and release the oxygen back to the air. I would like to see that if there's no such natural process, our life will take a distinct path. And in the artificial photosynthesis, currently, the dominant approach is based on PV and electrolysis process, which is using the photovoltaic solar cell that converts the light into electricity and use the generated electricity to drive up the productions of hydrocarbons and oxygenates. However, in our research, that we would like to combine these two processes in one unit, which is based on photoelectrocatalysis. Photoelectrocatalysis is heavily relies on the photoactive semiconductors that can harvest the sunlight and generate the electron and hole pairs. And those electron and hole pairs can migrate to the surface of the semiconductor and drive up the redox reactions. Photoelectrocatalysis can be applied into various applications. It can be used for environmental applications such as air purification or water remediation. It can also be used for fine organic synthesis, such as the glycerol oxidation to produce DHA, or methane oxidation to produce ethylene or other hydrocarbons. It can also be used for various solar energy conversion applications, such as carbon dioxide reduction conversion, water splitting to produce hydrogen and oxygen, hydrogen peroxide generation, and ammonium synthesis from nitrogen or nitrate reduction. So far, our group is mainly focusing on the solar energy conversion applications using photoelectrocatalysis process. Even though it has various applications, photoelectrocatalysis is a relatively complex process, which involves multi-steps ranging from the charge separation to surface catalysis. The overall efficiency of the photoelectrocatalysis is determined by the charge generation efficiency, charge transport efficiency, and surface reaction efficiency. Here, I would like to note that the time scale of electron-hole recombination is multiple scale faster than the surface catalysis process, which is process very difficult to control but plays a critical role in determining the overall efficiency of photoelectrocatalysis. In this regard, our group is mainly focusing on manipulating charge transport of semiconducting oxide to push forward the limit of the overall efficiency in photoelectrocatalysis. To better understand or to better manipulate the transport of semiconductor, we need to know what properties of the material that we can regulate. Actually, in photoelectrocatalysis or in the semiconductors, that there are abundant, huge amount of properties that we can manipulate to improve the performance. But those properties relevant to the charge transport are the effective mass of carriers, carrier lifetime, carrier mobility, and diffusion length. Also, the conductivity and the resistivity of the semiconductor, the distance or the width of the charge layer, and also the position of flat band or the surface states with shallow or deep surface states. Upon knowing the properties that we can regulate for semiconductors, I would like to introduce you that the general strategies in manipulate charge transport by photocatalytic design. For example, we can nanostructuring our semiconductors. We can make it into one-dimensional nanorods, two-dimensional nanosheets, or three-dimensional ordered macropore structures. With this unique structure, we can improve the light scattering effect and also facilitate the spectral charge separation. Meanwhile, we can also intentionally induce defects on the surface of our semiconductors. Unlike other processes that the defects is not desirable, we prefer the perfect lattice, but in photoelectrocatalysis, sometimes defects can be beneficial. It can promote the surface and solid interaction and also extend the carrier lifetime of photo-induced electrons, which can have sufficient time to react with the reactants. Certainly, we are also interested in crystal facet engineering. We can synthesize our catalyst with identical composition and crystallinity, but just with different facet ratios. In this situation, we can promote the charge separation spatially and also steer the reaction toward our desired products. Lastly, we are also interested in designing and fabricating heterostructured composites with 2 or even 3 photoactive semiconductors combined together, take advantages of their redox potentials and light absorption with facilitated interfacial charge separation. In this situation, most of the time, the heterostructured photocatalyst can achieve much better performance compared to a single counterpart. So this is the general strategies that people are using in manipulating the charge transport in photoelectrocatalysis. And in the following time, I will introduce you how our group using such these strategies to improve the charge transport in semiconducting oxide. First of all, I would like to introduce our study about the development of cuprous oxide photocatalyst thin films for carbon dioxide reduction reaction. With the development of solar fuel production, that cuprous oxide has been recognized as one of the benchmark materials in carbon dioxide reduction, in particular the solid gas phase reactions. However, when we're using it in such kind of reaction, it is still faced by 3 major challenges. The first is low stability. Upon the light excitation, the generated electrons and holes can either reduce cuprous oxide into copper or oxidize cuprous oxide into copper oxide. In this situation, we will lose its excited visible light absorption ability. So lose its photoactivity. And meanwhile, as a bulk semiconducting oxide, cuprous oxide itself usually cannot provide enough or abundant active sites for carbon dioxide absorption and reaction. Okay, and thirdly, it's about the low selectivity. Because the conduction band of cuprous oxide is very negative, so thermodynamically speaking, it is powerful that can drag the carbon dioxide reduction into various products, such as carbon monoxide, formic acid, or methane. Compared to other products, the carbon dioxide to methane conversion is extremely intriguing and attracting. It's mainly because methane is a raw material for the ethylene production. Once it's transformed into ethylene, it can be used for various industrial products or chemical processing. So But however, compared to other products, the carbon dioxide to methane require 8 electrons of charge transfer, which is kinetically more demanding compared to other products. So in this situation, our group wants to come up with one strategy that can simultaneously address these three challenges together. So after a thorough investigation, and we decided to code a copper-based metal organic frameworks on the surface of cuprous oxide using the top-tactic conversion strategy, which is relatively new. By using this method, we can coat a very homogeneous layer of copper morphs on its surface. I see the real image of the samples. Upon the top-tactic conversion strategy, we change the original red color of cuprous oxide into a green color. This green color is reflected by the copper morphs upon absorbing the water from the atmosphere. This color is very beautiful, just as the green leaf as we can usually or often think from the nature. And further, the TEM and also the corresponding EDS results suggest that we have successfully synthesized the cold shell structure with the cuprous oxide as the core and copper-based morph as the shell. Upon knowing that, we apply our catalyst in the carbon dioxide reduction reaction, and our results show that upon the morph coating, the carbon dioxide to methane conversion activity is significantly increased, and more importantly, the stability is also ameliorated. As for the bare cuprous oxide, we can see that after 3 cycles of experiments, that we almost lose all the activity in carbon dioxide reduction. On the other hand, with the morph coating, we can retain around 75 of the intrinsic or original activity after 5 cycles of experiments. And meanwhile, in photocatalytic carbon dioxide reduction, the stoichiometric evolution of products is always a focus by the community. As shown on the PPT slide, the produced methane and oxygen should be into 1:2 ratio. So to prove that, we did the time-dependent experiments, and our results indeed show that the produced oxygen and methane are in 2:1 ratio. This is very important indication, and it suggests that the photo-induced electrons and holes are fully participated in such a reaction. In the meanwhile, since we involve the copper-based morph in the photocatalyst design, which is a carbonaceous materials, we were wondering if the produced methane are indeed from the carbon dioxide reduction reaction. So to prove that, we use GCMS and the isotope experiments. We're using carbon dioxide with carbon-13 and oxygen with oxygen-18. The results collectively suggest that the produced methane are indeed from the carbon dioxide reduction instead of the parasitic reaction of the photocatalyst itself. Upon knowing that, we are now in a position to understand why we improve the selectivity and sensitivity. So the first and dangerous understanding is that we involve the copper-based morph in the photocatalyst, which is a porous materials. It should be able to increase the surface area for carbon dioxide absorption. To prove that, we did the carbon dioxide uptake experiments, and the results indeed show that upon the copper morph coating, we increase the carbon dioxide uptake capacity by 7 times enhancement compared to the bare cuprous oxide. In addition to that, we are also interested to know the potential transport behavior between the cuprous oxide core and the copper-based morph shell. To prove that, we first did the steady-state photoluminescence studies on our sample. For the bare cuprous oxide, it shows an intrinsic emission signal centered around 500 nanometers. Intrinsically, upon the declaration of copper morphs at the shell, in addition to the intrinsic emission signal of cuprous oxide, we create a new emission signal centered around 630 nanometers. So we're curious about where the new signal come from. So we plot the energy position of copper morph together with cuprous oxide, and we assume that the energetic electrons excited on the conduction band of cuprous oxide can transfer to the LUMO level of copper morphs. When the electron transferred and there's no carbon dioxide in the system, the electrons on the LUMO level of copper morph can recombine with the holes on the valence band of cuprous oxide and create a new emission signal. And here we would like to know that the energy difference between the lumen level of copper MOF and the valence band of cuprous oxide perfectly matched with the energy at 630 nanometers. To further prove that, we also did the time-resolved photoluminescence studies. We first monitor their emission signal at 630 nanometer. We found that, similar as the steady-state PL demonstration, that only the copper-based MOF composite materials shows a very obvious signal, but for the bare cuprous oxide, we can't detect its PL. And when we monitor their signals at 500 nanometers, and here, so we can see that both samples show signals but with negligible difference. So the time-resolved PL results agree well with observation from the steady-state PL, and it suggests that the photo-induced electron transfer from excited cuprous oxide to copper MOFs. This is very important finding. It suggests that the electron can transfer to the copper MOF, and then the electron can be utilized by the copper MOF and react with absorbed carbon dioxide to promote the carbon dioxide reaction. So as a fundamental study, that our research also extends the relationships between metal organic frameworks and metal oxide beyond their physics option, chemistry option understanding or type of interactions to now include charge separation. And as a proof of concept that our work ignites a quite, comprehensive attention from the community. But regarding the activity, our performance is still low. And we found that actually in such process, the overall efficiency of our system is still limited by the poor charge transport of photo-induced holes and also the limited water oxidation power of cuprous oxide. So to further prove the performance of our system, we try to assemble another water oxidation photocatalyst with our system and to prove the carbon dioxide reduction reaction performance. And we select out the benchmarking material of bismuth 1-date. But before we assemble the bismuth 1-date into our system, that there are plenty rooms for us to investigate the different types of bismuth 1-date and select out the best candidate. So in 2017, that my PhD group run by my Professor Mao published a paper in Nature Communication, which investigated the nanoporous structure of perovskite in photocatalysis. Such unique structure attract me a lot because it has many obvious advantages, such as large surface area, rich surface functionality, strong light trapping effect, and until recently, more and more groups noticed it has different charge carrier transport behaviors. But however, how about intrinsic carrier properties between the three-dome bismuth 1-date and the bulk counterpart? The understanding is very limited. For example, how about their difference in carrier diffusion length, charge mobility, and electron lifetime? So to answer that, we first synthesize the three-dome bismuth 1-date. From the ICM image, we can see the periodically ordered pores within our samples. And with the fine structure analysis, the first information that we would like to talk is about the ultra-thin internal wall of the structure. When we synthesize the catalyst into nano regions such as 5 to 10 nanometers, it generally shows the quantum confinement effect, which could enlarge the band gap of the semiconductor and increase the thermodynamic power of the photo-induced carriers. So to prove such effect, we first did the UV measurements of our samples, and we found that compared to its bulk counterpart, the three-dome bismuth 1-date shows a blue shift of light absorption, indicating its enlarged band gap. And upon combining with the UPS results, our results show that compared to the bulk counterpart, the quantum confinement effect uplifted the conduction band position of bismuth 1-date and enabling it thermodynamically enough or powerful to reduce proton to generate hydrogen. So to prove such effect, we did the hydrogen evolution experiments for our two samples with the scavenger of holes, and we found that the three-dome bismuth 1-date can achieve a very efficient hydrogen evolution and it's very cost stable, but the bulk counterpart shows limited performance. So this is the first time for us to report that the three-dome structure of bismuth 1-date can induce quantum confinement effects, which enable it or shift it from a water oxidation catalyst into hydrogen evolution catalyst, which is very meaningful for the following studies to design the one-step excitation for bismuth 1 for overall water splitting. And upon that, actually, the second fine structure analysis that I would like to share is about the distinct lattice structures between the interconnection part and the internal wall of the 3-dome bismuth 1. I've introduced in the introduction that crystal engineering is one of the general strategies in manipulating charge transport of semiconducting oxide. So we were wondering if there is a potential energy gradient between the interconnection part of bismuth 1 and also the internal wall. To prove that, we did the Kelvin probe force microscopy, KPFM, and we did a line scan across the interconnection, the wall and the internal wall. And we found that there is a built-in electrical field with an upward bending from the internal wall to the interconnection bar. It suggests that the photo-induced holes will easily extracted to the internal wall, and the holes will accumulate on the interconnection part. Just facilitated the special charge separation of photo-induced carriers and contribute to the enhanced charge mobility. To prove that, we also did the time-resolved microwave conductivity measurements, and the results suggest that indeed the 3-dome bismuth 1 shows an enhanced charge mobility compared to the bulk counterpart with around 6 times enhancement. But even though for this situation we enable the hydrogen evolution, but if without a host scavenger, our system still cannot produce hydrogen. And upon the investigation, we noticed that the limited performance for overall water splitting, which is mainly because the poor charge transport of the carrier and also the limited reaction kinetics of proton reduction. So to resolve such problem or challenge, we further decorate our material with rhodium and chromium co-catalyst, and the results show that upon the co-catalyst decoration, we intensified the building electrical field with the contact potential difference from 25 millivoltage to 50 millivoltage. It suggests that with the co-catalyst decoration, it will promote the band bending over the surface. So also further promote the charge separation between the interconnection part and the internal wall of the 3-dome bismuth 1. And with this optimization of the co-catalyst decoration, we achieved the one-step excitation of bismuth 1 for overall water splitting with stoichiometric evolution of hydrogen and oxygen. The apparent quantum efficiency is around 0.4%. This is also the first time for us to report that bismuth 1 can be utilized for hydrogen and simultaneous production of hydrogen and oxygen, which is very meaningful to the community. But however, so far that we introduced our development of the photocatalytic system, but this is a system regarding the efficiency is relatively low. So in addition to the material design that we have to revolutionize the reaction system to improve the overall efficiency. So based on this understanding, that we step into the photoelectrochemical process, which take advantages of the sunlight and also the electrical energy to improve the overall efficiency of photocatalysis. And in this area, in particularly for the water oxidation, the bismuth 1 is also, has been regarded as the top performing materials. But however, its ultimate performance still limited by the poor charge separation, which is mainly limited by small poron and also the per surface water oxidation kinetics. So to improve the performance of bismuth 1 photoanode in photoelectrochemical water oxidation, we involved the small poron engineering in this system. Poron is a relatively physical concept, which is interaction between the charge carriers and the lattice of the semiconductors. If we take in titanium or bismuth 1 for example, when we shine the light on the samples, it can excite the electrons, and such electrons can interact with the lattice of the semiconductor. Once they interact, the electrons can be potentially accommodated by the lattice and cause the lattice expansion. Once such interaction or the quasi-particle form, we call small poron. The small poron is generally regarded as a localized band energy states. once the electron be trapped by the polar states, it requires further thermal energy to re-excite back to the delocalized band states and move forward. In this situation, it will significantly drag the carrier mobility and induce the strong charge carrier recombination. So to better understanding property of the small boron, we would like to introduce or contrast it with large boron. Small boron, also called Horn's boron, is interaction radius generally just within 1 lattice unit, and it has a thermally activated Hoping mobility with value much smaller than 1 centimeter square per voltage per second, and this mobility generally increased with the temperature. On the other hand, for the large boron, we also call frog-leaf boron, its polar radius generally crosses several lattice units, and it has a free carrier mobility with value much larger than 1 centimeter square per voltage per second, as its mobility generally decreases with the temperature. So here we can see that there are distinct properties between the small and large borons. Based on this understanding, we first did the temperature-dependent conductance measurements on our samples. We prepared 2 samples with and without phosphorus doping. And we both increased the temperature, and we found that the conductance of both samples increased with reading the temperature, indicating their Hoping conduction behavior, no matter with or without phosphorus doping. But when we feed the conductance with the temperature following the Arrhenius manner relationship, we found that with the phosphorus doping, the activation energy of boron Hoping is decreased from 434 to 273 milli-electron voltage. It suggests that the boron is easier to be hopped from among the lattice of bismuth 1-day, just promote the charge carrier transport behaviors. And to prove that, we also did the time-resolved microwave conducting measurements, and the results indeed suggest that upon the phosphorus doping, that the carrier mobility increased by around 3.2 times. Upon knowing from the experiments, we also did a theoretical understanding on the boron Hoping behavior within our systems, and we found that upon the phosphorus doping, that we changed the boron Hoping behavior within the bismuth 1-day and reduced the Hoping barriers, with the lowest activation energy goes to 239 milli-electron voltage compared to that of the 268 of the pristine bismuth 1-day. And it suggests that it will require less activation energy for the boron to hop from one reaction coordinate to the next. So it can promote the boron movement. And also we determined their binding energy or the energy position of boron states, and we found that upon the phosphorus doping, we uplifted the energy position of boron. It suggests that if the charge or the electrons confined with the boron states is require less energy or much easier to re-excite back to the delocalized band states and move forward. So this is the first time for us to report that the phosphorus doping can decrease the boron Hoping activation energy and in turn increase the charge transport behaviors. And by this boron engineering, we reduce top performing performance for photoelectrochemical water splitting with an applied bias photocurrent efficiency of 2.21% at 0.6 voltage with RHE, which is one of the best performance that have been reported in 2022 or before. And with the performance, we can have a look at the recorded video. Upon the light illumination on the bismuth 1-day, we can see its surface shows a robust water oxidation process. So this is about our the first study in boron. But when we do this work, we found a problem is that no matter how do we optimize our samples, the experimentally obtained value for boron Hoping activation energy is always larger than that of the theoretical counterpart. Why? Why is the situation? Then upon the investigation, we noticed that the bismuth 1-day has many intrinsic defects, such as vacancy, oxygen vacancies. And such defects can columbically interact with the negatively charged small boron. So in this situation, it will drag the boron and form the bond boron. So to understand how the interaction between the oxygen vacancies and the small boron, we induce the hydrogen doping or substitution of bismuth vanadate, which substitutes the oxygen vacancies of bismuth vanadate, passivate the bismuth vanadate with the oxygen vacancy defects, and induce a much improved performance. In particular, it achieve a better front illumination performance compared to the back. Because mostly due to the boron interaction, the electron transport in bismuth vanadate is poor, so the back illumination generally shows a better performance compared to the front. But within the hydrogen treatment that we remediate the boron behavior, and we achieve a better front illumination performance. And this finding is particularly meaningful to the tandem research. Maybe you know that when we do the photoelectrochemical water splitting, we can make a tandem cell. So the front side of the photoanode can generate oxygen, and the front side of the cathode can generate oxygen. So if we have a better front illumination, it's extremely beneficial in such device. If we can only achieve a better performance from the back, then the front side of the material cannot contact with the electrolyte, so we cannot use in the tandem device. So that's why this power engineering is very beneficial to the tandem device development. And with the experimental and theoretical studies, we again suggest that upon the hydrogen treatment, which sit around the oxygen vacancy of bismuth vanadate, it promotes polar hopping from the defects to the first vanadium, but more importantly, it promotes the polar hopping from the first defects. The first vanadium side close to the defect to the second. So that's why it improved the charge carrier transport, in particular the electron transport with the bismuth vanadate. So overall, we have summarized our understanding in designing the semiconductors or manipulating the charge transport of semiconductors in photoelectrocatalysis, and published our understandings into some reputational platforms, which has attracted quite amount of attention from the community. And also our research articles also being published to the reputational platforms. Some of our works also being selected as a front cover, and also the very famous research media Eureka Large Science also reported some of our works in this research area. So toward the end, I would like to thank all the audience attention at the time. I do hope that in the future we can collaborate with our talents in Indonesia to contribute to the research community and publish papers. And also, if possible, I know that Indonesia has abundant resources of sunlight and sea water. If we can apply this process to split the seawater and generate green energy power for our Indonesia society, I think it will be very beneficial. So if you have interest, please feel free to email me and we can initiate some informal talk. Let's see if there is a room for us to collaborate. So that's all about my talk. Thanks again.
Thank you very much, Wu Hao, for your eh, insightful thoughts. Some things that we learn from here is about the advancements in this field that now it's like an imagine maybe a few years ago about the concept of the polarons. Indeed, it is still new. Some of our researchers in Indonesia start doing this. In Department of ITS, we have Professor Yuli Kusumawati, which is also our coordinator for the undergraduate programs, who also concentrate in this field. I mean, the polarons in collaboration with her college in Singapore. And these ones, I hope that it will by this by these presentations and by this interaction, I hope that it will open the opportunity for us, not only from the chemistry department in ITS, but also from the community in East Java, because for your information, in East Java, there are several, what can I say, like a big universities here, we, many universities, but some of them are quite large in terms of the academic staffs and also students. Let's say, for example, in Surabaya, we have Universitas Airlangga, ITS, Institut Teknologi Sepuluh Nopember, and also mm, Universitas Negeri Surabaya, which is Surabaya State University. In our neighboring city, Malang, we have a State University of Malang, Brawijaya University,
Yeah.
Islamic State University, Malik Ibrahim, Universitas Jember, all is the public university which they have colleges or staff who concentrate on photocatalysis. So actually photocatalysis is quite popular in terms of the focus of research in the East Java province. So hopefully what you share to us will improve our understandings and opens our horizons about the current progress in photocatalysis. And we thanks for Dr. Hao Wu for his offerings and welcomes. In case in the future we can have more collaborations. I myself, as a head of Department of Chemistry, hopefully will implement what we have started during your visit in Department of Chemistry this week, especially implementing what we have discussed with our vice rectors. Thank you very much for your attention, and again, thank you very much for your sharing, Dr. Hao Wu. Hopefully we can meet in another times, and hopefully we can also invite you in another webinars held by the Himpunan Kimia Indonesia, each of our branch, or even from the centrals. I mean, Indonesian Chemical Society, the central management. Thank you very much.
Thank you.
Goodbye, good afternoon for this time. Thank you very much.
Thank
Bye
you.
bye.
Bye.
See you later.